paper final I'd like to give in this course. So we need to find a method and time to accomplish that. So we've heard a couple votes of not during finals week.
Actually, can I change mine? Because I won't be here Thursdays and Fridays now, and I think of it, so.
All right. Any other comments from
Take-home test
Just do a
sounds
take-home
best.
test, then you don't have to worry about setting up a time.
True, but there's content I want to make sure I get on there that is difficult to present in the online.
So we'll have it a paper one.
You have a paper copy to take home.
Hand out like the last time,
That's a good idea. There we go.
second last time in class, and we have to hand it in next week.
Except that I want to give you only 1 to 2 hours time to do that.
Oh,
Here
yeah.
are books.
It's open book, open notes.
Are you going to give us a bank again?
A what?
Like the question banks which you used last time? Or review those?
I'll give you topics, but not actual questions. Another option is that if we could group those into different, that I could have office hours, if you will, to give that exam as long as it's not 30 individual times. In other words, I could have 3 or 4 different time periods so that the reason it's a bit challenging is I understand that some of you may not want to be around during finals week or have other stuff going on, but I still have content on the last class period that I want to include on the exam. So are you guys okay that if I put up different test times with your input, would that work all right? And then that way, if someone wants to take it before finals week, you can. And if someone else says, you know, I'm just too busy, I'll do it during finals week, that would be fine also. All right, good. We'll move on to the next items. Today we're going to talk about 3 basic categories of information: SPC, statistical process control. There are a lot of different control charts. I'm primarily going to focus only on one set, if you will, called the X bar and R chart. In my opinion, that if you have at least an intuitive understanding of how that control chart method works, you'd be able to gain understanding on how to do the other methods as well. I will also talk about them, but I will not expect you to be able to understand those without notes. Process capability, these are the 2 indices, if you will, of a numerical value of comparing performance versus a specification range. In some cases of supplier quality, that is a very significant indice. In some situations, there are organizations that will specify not only a specification range, but they will say what process capability you have to demonstrate as a supplier as part of your requirements to ship that. So I've, some of the positive head nodding, I guess that's done at your organization. Are you expecting that of your suppliers, or?
Maybe not suppliers of the components or extrusions, for example. But
okay.
When we specify when we're developing specifications for the equipment that we purchase,
Oh, certainly.
they have to perform within certain CPK.
Right, that was, I wasn't actually going to talk about that today, but that's an excellent point. That when we get to that, I'll try to reemphasize it. But the idea is that if you, many manufacturers of equipment will put on their sales literature that they can perform plus or minus 4,000s, 10,000s. And it's very convenient as a buyer to just go, oh, it's in the sales literature, therefore it will do that. Those of you that may have actually checked that before you buy it, or maybe more unfortunately, you buy the equipment, install it, you start making parts, and you're like, wow, this just isn't doing what I thought it was going to do. That's a little too late because you've already bought the equipment and installed it. So and I think, for example, 3M is very studious with that they won't even, you can't even put in a requisition for a piece of capital equipment unless you've demonstrated that it's able to do that. So it's a great piece of advice, not only for businesses, but your own personal life, that if you're expecting, I'm not saying you need to check every microwave or toaster that you buy does this, but you need to have some type of proof that it does that. So one way to do that with a piece of equipment, if it's a machining center, you can actually ask the supplier to make 25 or 30 parts representative of what you're going to build, and measure those to get a process capability of that.
And then re-verify it when you get more, because a lot of times they'll make good parts for your initial
Correct.
sample.
I call that the state fair syndrome.
Yes.
My sister was in 4-H, and so I was the tester as the little brother for all the items that went to the fair. And I got to eat a lot of rejects that didn't go to the fair, but they were still pretty tasty. But nonetheless, the state fair syndrome, as I call it, is that the supplier will make parts and then sort through the best ones and then give that to you as a representative sample. And that's one reason that I've suggested that we plot the normal, plot the histogram of that to see if that looks like a normally distributed population, because otherwise, if they do that too much, the variation will look suspicious. Another way to get around that is to, if it's a significant piece of equipment, to actually go watch the trials yourself, if that's possible. That's even better, because it's fun watching the supplier actually fire up the machine and try to operate under the, because your parts typically are not the same as their sales literature trinkets that they have at the trade shows, even though they may look a lot alike. All right, so these are the topics we'll cover, and this example X-bar R chart, we're going to try to execute a trial here in our room to illustrate the use of an X-bar R chart conceptually, and then we'll use that data to calculate our own CP and CPK, and then we'll do a statistical inference as well. So we'll go ahead and move into our topics today. So SPC stands for Statistical Process Control. Does anyone remember from our first class in August who we can attribute control charting to? We'll start with the student population, see if anyone can remember that.
Deming?
Nope. Good guess though, because Deming was Chris Schuhart. So that was, I believe, 1924, if I remember correctly, that he's attributed with coming up with this idea of creating a picture, if you will. So it's a graph or picture of the process as it's performing. So we'll go back over this a bit later, but there's some vocabulary words we'd like to look at. Typically a classic X-bar R chart has a series of lines on that. Basically, there's a central tendency, which is based off of the mean of those samples. Maybe a better way to describe that is to be the grand mean. So you typically, when you create an X bar, where that comes from as well, is this is a sample size typically greater than two or greater. So it's not an individual. So you take the average of that sample or mean and plot that observation, and it's a time series. So the reason that time series is important is that we're looking for a trend over time. So we're going to plot our average of that sample. If we pull 5 parts from that process would plot that point, and the reason that Schuhart liked this is that by plotting the points, those points with a graph, it's easy to communicate to someone that if it's outside these control limits, it is likely that there is a assignable cause. Does anyone know what we mean by assignable cause? If it's outside these control limits, what do you think the phrase assignable cause indicates? Sometimes we might use the word special as well.
Something changed in the process that's resulted in a different value. Yeah.
Right, or said another way, if a process is operating under the conditions it always has, there is common cause, which is just random variation that is just due to a random event. It's not attributable to a particular assignable or special cause. All right, so you establish these control limits. Typically, basically it's plus or minus 3 standard deviations from the central tendency. So what happens is, if you're outside of that control limit, it's highly likely that something special or unique has happened to cause a process shift, is another word we're interested in. So Schuhart recognized that by making a picture of this, it was easier to communicate this to machine operators and other employees as opposed to strictly giving a table of numbers. Does that kind of make sense to everybody? That if I had I could just as equally have we have a sample, and then we have part 1, 2, and 3, and then we'll have our average. So if we just have a table with those numbers, it's difficult to pick out those trends quickly and easily. If you plot these, and there's a series of rules of thumb, which we'll talk about in a few moments, that can give you clues that something has gone on. All right, so that is Schuhart. We'll go into some of the benefits of control charts, and we'll come back to some of these terms yet again. So some of the things we're interested in include the average level of quality characteristic. So one example could be we're cutting parts to length. That could be in centimeters. So our quality characteristic is what we're measuring. That could be something like length, it could be weight. We're also interested in the variability of that quality characteristic. And we're also interested in how consistent we are. Another key keywords that are worth putting in here is it helps us to monitor that process. As I said in before, that it's a graphical way to communicate that. So as I said before, there's a difference between common and special causes. Is everybody comfortable with the difference between those? Common cause are what people would associate with random variation. Special is that there's some event that has changed that caused that to be different. So some examples of special cause would be a different employee operating that piece of equipment, material changes. So be it Daktronics had a change in material composition, and then we started getting during a press brake operation, there's like an orange peel or it fractures when it bends. So that caused a lot of commotion for us today. So that is a material change, even though we were operating the press brake with the same tooling, the same operator, the parts change. So material is a classic example of that. What are some other special causes that some of you can think of that causes your performance to change? So from an academic standpoint, what are things that impact what type of grade or your score in a class might be? Right, so the amount of other work that you're performing can impact that. So the work analogy to that would be workload. There's more work to be accomplished, so you get to be rushed. Any other examples that anyone would like to share?
Coming to class.
Yep, whether you attended the training session, if you will. Scrap rate can make a difference. All right, so let's move into some other comments about that may be helpful for us. All right, one thing to recognize with control charts is we use this phrase quality characteristic, and frequently most people associate that with a physical part that you're making, right? And the reason I'm making this distinction is, if you remember right, we've talked about failure modes and effects, and we also talked about control plans. And in those control plans, we talked about input or output variables. So an output is the result of us doing a physical value-added activity. So like, let's say that we're on a machining lathe. We take a round bar stock, and then we turn an outside diameter, and then that might be the quality characteristic of interest. That's what that's the output. Now the other aspect of it is you could measure the input variables, all right? Many people overlook that, but in some situations, measuring the input variable can actually be more valuable for the fact of two reasons. It may be less expensive, and it may actually be easier to observe. So one example at Daktronics that I'm going to attempt to draw some type of a crude LED here, and I'm going to get some of my terms wrong here, I'm sure, but so there's actually a little wire that is connected across the top of these two posts, and we use this phrase of wire bond. So we're interested in how well that wire is attached to 2 points. The only way to really measure how strong that is we destructively grab onto it and yank it and rip it. So when you do that, that's the specification, how strong the wire bond should be. But the only way to sample it is to destructively test it. So once it's destructively tested, we can't use that LED anymore. So then, when you're sampling a process, all you're going to be able to get is the observations of the parts we threw away to test. So another way to do that is the input. In other words, we can, through a designed experiment, figure out what factors or inputs impact the quality of that strength of that bond. And once again, I apologize, I don't know the exact terms for this, but there's like a force and a duration of that probe has imparted upon that wire to create that joint. So that is I'm advocating that that is a better place to perform a quality control check, because you can measure the force applied to create that bond and use a automatic data collection system to track that. And then you could actually have live data of this lot of 1 million LEDs had that particular process done to it. Does that make sense to everybody what I'm talking about? A more simplified example could be you're making cookies and the temperature of the oven contributes to how the cookies turn out. So tracking the temperature of that oven could be the input variable. So that could be the quality characteristic of interest. So the point of emphasis I'm trying to make here is that control charting can be done on physical parts that you buy from somebody, but it can also be done on the processes to make those parts. Okay, so that is I think at times many companies forget that you can measure the processes, not just the products themselves. So is Brian have you guys officially changed your company name yet, or?
Tomorrow.
Tomorrow, okay. Because I get emails from you and I'm having trouble keeping track of the.
Tomorrow was the Spark.
So today I can say, does Onyx do any in-process control instead of the actual physical object as I've described here?
We do it more upfront, sometimes when the first article process, but where you'll define that, basically validate that with these process parameters, these are the outputs of the process. And by doing that, you've said, all right, if we run in our operation range from this limit to this limit, we produce good product. So as long as we know our process is going to operate in that range, yes.
But you don't actively control chart those.
No.
You just know that if you're within those parameters, you'll have good product.
Yes.
Okay.
I'd like if we had more active reporting. A lot of times those systems can be very expensive for data acquisition.
That is true. But I think the point is still valid of
Yeah.
recognizing that processes make products. And if,
Especially when Onyx, we don't make large volumes. But the larger the volume you
Correct.
make, the more it leads towards doing SPC on your process rather than verifying or checking your product.
certainly, and with Daktronics having placed over 2 billion LEDs in our
Exactly.
lifetime, that would be considered high volume.
Very high.
Any other comments from anyone about using process capability measurements as opposed to the end product?
At Larson's, for example, we checking the dying level of the extrusion before we putting it in our hot melt process to make sure that it's going to stick very well to the surface. Instead of ripping it after.
Oh, the peels,
checking
right,
it stick.
the adhesive
Yeah.
properties. Valid point. All right, so that is the reason I went into that relatively long-winded conversation is that authors of our book talk about the selection of variables. So when you have a typical in engineering drawing, there's hundreds, if not thousands, of dimensions that you could track on those parts. So the challenge you run up against, which Brian alluded to, that you only have a finite amount of time and effort and money to track these variables, and which quality characteristics will give you the most efficient view of the achievement of those quality characteristics with the limited resources you have available. All right, so another Daktronics example, we get a lot of molded plastic parts, and when you have a molded part, it's made with a tool which doesn't change over time, but the parts may warp, or the processing characteristics are impacted by, let me back up, the finished part is a result of maybe 7 to 10 different processing parameters. So one goal we're trying to accomplish is, what are those quality characteristics that would give us the health of the process, is how I describe it, and trying to collect that. So that would be part of that selection of variables. What are some other considerations that would impact your choice of variables to track?
Fit and function. I mean, you might have so many different parameters in the same product that in assembly, half of them are really irrelevant. So you're selecting only the critical dimensions, critical characteristics for the assembly itself.
Yes, that was the next thought I was going to piggyback on, is that if you have an individual component, like let's say this dry erase marker, the specifications may tell us what the outside of this lid, the outside diameter is, but it's most important the diameter related to its mating part. Does that make sense? So while we may actually evaluate the outside diameter, we're going to be more interested in the relationship of those two parts in the assembly. What are some other considerations from a quality standpoint related to selecting of variables?
Sometimes it's kind of difficult to select them up front. As a recent example is we've been using SAE hardware, just a flat washer, and in the design, this flat washer was giving us some clearance between the other two parts. And when specifying the hardware to our supplier, we just specified the SAE hardware. Well, the design tolerance was tight enough where the variance allowed inside that SAE hardware caused a part collision 3 years down the road when the supplier changed out to minimize the amount of material that they were putting into these flat washers. And it took us a while to figure out what exactly was going on, but kind of one of those things where that parameter was something that was critical to quality, but not considered upfront.
So that is one of the considerations when you're trying to create control charts, is by experience. It seems like everything's going fine. Same type of thing happened with us with this change in our the chemistry, if you will, of the sheet metal. We were having too tight of a bend radius. For 3 years we've done it without significant issues, and we received a particular lot that it was so bad that with your bare hand you could break the part. It's like, it was frustrating.
Although impressive to your friends.
It's
Failure mode and effect analysis.
right. So ideally, we're talking about looking. This is kind of like looking in the past. What problems did we have previously? FMEA is looking to the future, because we want to anticipate where we have our issues. So if you remember from FMEA, we come up with a RPN, a risk priority number. So those would be ones that score high, meaning that there's a higher risk of pain and suffering, for lack of a better term for that. So you want to address those earlier. What are some other ones? These are great ones we've had to this point.
Customer request.
Right. There are situations where the customer just says, I want this measurement.
This kind of piggybacks on his, but just critical to quality. Things you've identified in the design phase as critical to the function of the device.
So going back to this customer one, all of us are customers, and in many cases, we're suppliers to other people. So I encourage you as a customer quality person to suggest as reasonable as possible requirements. So it kind of makes sense that it's, we all have had a customer who has asked for something that we can't possibly understand why it's useful. I'm just encouraging you to be open-minded when your supplier rolls their eyes to explain why it's a valid item. And at the end, we all have to recognize that the customer is paying us for these things, so hopefully they understand that there's potentially some costs associated. Any other things, that considerations related to selection of variables? We'll move on to the next one of rational subgrouping. All right, so just a quick refresher. We established that using the central limit theorem, which says that if you have a process which creates parts in a non-normally distributed manner, that if you take a sample from that and average or plot the means of that, over time it will look like a normally distributed. So the example I gave is if you're flipping a coin, or let's say rolling a dice, each of the 6 sides has an equal chance of happening, so that is a normally distributed item. But if you were to take the average of 2 rolls, over time that will have a more of that standard normal look. Typically it's more of a triangle until you get it into higher quantities. But nonetheless, we've established that taking a sample allows us to get a normally distributed process. That is advantageous because many of our inferences are based on the assumption that it is normally distributed. With that said, we're going to be taking a sample, and if you're taking a sample, how do you decide how you group those parts in that sample? So one of the examples we talked about related to taking a sample looking for a process shift was that we might have someone working night shift, we might have a material change, etc. So what are considerations as you have a process that's running around the clock? I've already given you 2 that you need to consider for rational subgrouping. See if anyone, oh.
It's a machine, you might go startup time and turn off time. On off, start and finish.
And are you advocating that you exclude those during the startup and or your?
No, not necessarily.
Okay.
Possibility.
Maybe I should say it another way.
The time of the shift, because especially we observing that day in, day out, we have a peak usage of the air in the facility, and performance of certain pieces of equipment will change with this shift in how many pieces of equipment is actually are actually using this app. So
Demand changes.
so demand changes,
Okay.
and that will change performances of some of it.
So let me back up. Is it clear to everybody why a subgroup is important? Because if you don't understand this concept, this is all just going to be like Marcy, comfortable with that?
No.
Nope. All right, so let's say that my rational subgroup is once a day I'm going to take 30 parts that I collected just kind of throughout the day, put them in a bucket, and I'm going to send them to QC or QA, and they will check those tomorrow. The problem with that is, let's say that I've collected those over an entire day, and I have 3 shifts in a day, so I'm going to have parts made by 3 different people in this bucket. And if I'm looking for a assignable cause, if I spread that collection in too big of a net, I'm going to lose some of this stratification or granularity that could give me information about what's taking place. Does that make more sense? So what we're trying to create here in this little list are what are considerations to consider of how to choose your subgroups. So we've established the time or shift. In other words, we want to limit that to a particular shift, maybe by hour.
Consumable tools.
I'm just going to throw that under a tool life concept with that you should not sample parts across different, like if you have an inserted cutting tool. It's a good suggestion.
Equipment number or
Say again?
equipment number or operator?
Tool source materials.
How many parts the tooling makes at one time?
Yes, that's it.
Cavities?
Yes, that's, what's the other word for that in injection molding? There's multiple cavities. Is that just the right word for it? Like a, what do you call all the parts that come out of one shot, if you will?
I guess a
One
shot.
shot, but multiple cavities.
It's multiple cavity, right, but it's not family, is it?
Tree
Tree.
family.
All right, does that make sense to everybody? In injection molding, especially if you're making small caps, bottle caps are a good example of this. You might have 8 or dozen, 16. The injection mold tool shoots all of those in one tree where they're all connected with gates, and then all those parts fall into the bin. It's desirable to make that one subgroup if you capture all of those parts.
The ones that,
That's a very good example.
especially for cavities, the ones I think you're bound to see in from the quality side is you'll get a result where you're having 50% fallout, 25% fallout, or 75% fallout, and it could be random chance. But a lot of times when you're into manufacturing things, 5, 6 injections, when they do hit solids on quarters or halves, it's a very quick jump to this is why, without a lot of investigation.
You're
It's
talking
not
about,
Which
guaranteed,
cavity it is.
but,
say the example again?
so if you are receiving parts and you're finding, look, I have 50% on the whole lot, I just inspected 100 pieces, or I had 25 pieces that failed for the same defect out of 100 pieces. When they're divisible by halves or fours,
Oh,
it's
okay.
an easy jump a lot of the times to say, hey, let's check, is it that? Because it's
Is
not
it a
very likely
cavity?
it lands on the quarter. It could, but it tends to lead towards the process parameter that way.
That's why they number the cavities
Yep.
in the mold too, just for that reason.
Right, because it is possible that maybe one of the 4 cavities has an issue.
Right, and the other 3 do not.
And so if there's they're divisible by the number of cavities in that mold, that's a good, yes. So we were talking about the same thing from just different angles.
Yes, it's just something, I've seen it at least 5 times in the last year where that can jump out at you. Where it's a set fraction that always comes down. If you populate 16 parts, or 4 parts is easier, and you have a 25% defect rate, chances are, one of them isn't getting populated right, not the whole population.
And that's why if you have a large enough part, it's nice to have a cavity number
Yes.
marked so that you can see that easily. Yes, good. Scott, any other subgroups that are?
Other than injection molding for dual sourcing, a lot of vendors will have multiple, or even injection, they'll have multiple resin suppliers. So you need to understand your vendors' variables before you create your subgroups. Because you could see the same thing where you're getting, this number is always failing, but it's not due to cavity, it's random cavities, so the material, yeah.
So the other comment I'd like to add with dual source is it could be material, it could be location. And sometimes that can be very frustrating if your supplier consolidates their shipments before they send it to you. So if it's coming from multiple plants and it's not marked, that would tie back to that half or 1/3, whatever the case may be on that. Yes, good distinction. Any other subgroups that?
Like time or shift, I think is pretty important. That one's come up several times. We recently actually just had a problem where we were getting all kinds of fish eyes in the paint, and it turned out it was only happening on day shifts because in a cell not too far away from where a air inlet was for the paint system, the gal was using a silicone spray to be able to slide rubber grips on easier. She was only doing it during the day, but.
Well, I'm very impressed you're able to find that. It's hard enough to find the problem with silicone, but then to have it with the air intake. You may not even be in the same building as what's, or room, definitely.
So yeah, she was actually going to the Churchill Walker for maintenance and getting it.
You did very good car.
Yeah.
Corrective action.
I won't ask you how long it took to find that.
Took a while.
Yeah. We're still missing one that I think is sort of up here, but I want it to be more explicitly listed. Season, we're getting closer.
Yeah, that's fine, that's sorted. I was trying to get sorted.
I'm just going to put temperature and humidity.
Environment.
Yes.
Environment, yeah.
The reason I'm going to mention that is it is interesting to me with all of the cost of recording temperature and humidity is ridiculously low, and yet remarkably the number of companies that actually track that is also remarkably low. So I think I gave you guys.
Like the food processing industry, that's like everything. Those types of things are very critical.
But even in metals and plastics, like composites, paint spraying, tremendous impact, and there are many facilities in South Dakota that are not climate controlled, and yet, or even the ones that are climate controlled, you can drive your humidity down real fast because we have these switches from air conditioning in the summer to heating in the winter, and I'm guessing there's a lot of defects or nonconformities that occur because of transitions from season to season, especially in places like South Dakota where it so abruptly switches from one to the other.
We had a vendor overseas that this kind of indirectly relates to environment or season, but we had a vendor overseas at the previous place that I worked that we couldn't figure out why one of their production facilities that looked exactly like all the other ones in different areas in China had a problem with material in their paint, like foreign material in their paint. And we found out that it was because they were leaving their doors open, their dock doors open during the hottest part of the year. And then there was a train track that went by and they had, I don't know if it was coal trains or whatever it was, but that was what was getting in their paint. So, I mean, even that kind of thing, you know, can affect your
Yes, that would be
part
the
performance.
environment, loosely. So what I'm getting to is that I'm an advocate of breaking your observations into the smallest pieces possible. But just because I'm saying smallest possible, don't just do it in small segments. You need to do some thought of what are the likely impacts that I already know will influence my manufacturing process. So time and shift, you almost always need to take that into consideration. You don't need to be cautious if you have a process that there's wide variation during startup, and then it stabilizes out and then shut down. Be careful where you're grabbing your samples for that. And let's see, what are some other? Operator and equipment, those are good ones. The cavities, the dual source, we've already mentioned those are great ones to consider. So basically the goal here is to, we use the phrase rational subgroups. We're going to intentionally think about how we're going to sample our for our control charting. I will add another comment related to that is right now we're talking about making control charts based on samples, but even if you are just doing a process capability or something of that nature, it's helpful to add tags, if you will, to those observations. So even if you don't separate it out to begin with, it's good to overlay your observations with temperature and humidity, time of day, operator number, and then after the fact, if you need it, you can already pull on that. The reason I'm saying that is once you collect the data, it's almost too late to go back later and go, now was that Jerry that ran those parts or was it Shannon? And we don't know because they're already thrown in the bucket.
If somebody screwed it up, it was probably me.
And so that is rational subgrouping. All right, next thing we're going to talk about is sources of variability. Incidentally, hopefully we recognize that we just listed a whole bunch of those. All right, so those are variability possibly from lot to lot. But we're also interested in the piece-to-piece variability. So going back to the injection molding, we have a family of cavities. We shoot parts that those parts fall out into a bin. We're interested in how much variation is there from part to part or cavity to cavity. We're also at times interested in the variation from part to part out of the same cavity. So I want to make sure that everybody's aware of that type of variation. Incidentally, on our chart on page, practicing my Roman numerals here, X is 10, is that right? Some big discussion in my house with my kids of what is the correct Roman numeral for 9? Is that IX, not V4?
It's IX.
So what is the maximum number of 3?
3
3 is
past
the
it.
max? All right. Thanks.
Did you win or lose that?
What's that?
Did you win or lose that conversation?
I just stayed silent watching my 8th grader and 2nd grader argue over that.
That's funny.
Maybe I should record our conversations at our just for entertainment purposes. All right, so nonetheless, on page X10, which is kind of interesting noting that you have different descriptions of the types of variation. I'll draw some of these up here to start with. So here we have within variation. So I'm going to list these, but as I list them, they're going to get smaller. I don't know if you can see that at the back, that the process gets to be a smaller lump. So if you take that away, then you're left with your lot to lot variation. So if you have within stream, then you have stream to stream, smaller. I'm going to skip down here a little bit further. You have your, what's called inherent process variation. You also have measurement variation, which is broken out into the equipment and then the operator or human. So recall we talked about measurement systems analysis. As you start measuring parts that have more precision required, then your equipment needs to be able to detect that variation as well. All right, now we're going to define two different classes of control charts. You can create a control chart or watch a process related to variables. Variables are what type of things?
Measurements?
Correct. Some type of continuous scale, typically. So the type of variable control charts that you will see are X bar R. Talk about that in more detail. We also have run charts. QSUM is one of those obscure ones. So moving average, exponent,